Good morning, good afternoon, good evening, class. This is Mr. Arosena. Today we start our study of scale drawings and models in math. So first we're going to start a review on what proportional reasoning is. It's something we talked about in probably like Math 9, maybe even earlier than that. I definitely know Math 9 we talked about it. So a proportion is basically what a statement of equality between two rates or two ratios. That's kind of what they say here. Let me highlight that for you. A proportion is a statement of equality, color, between two rates or two ratios. So basically it means that if I know the ratio of one object, then I can use that ratio to make copies of that object in different sizes. Okay? So a ratio is a comparison between two numbers with the same units. A rate is a comparison between two numbers with different units. So let's do the first example. Okay. The ratio of the length to the width of a rectangle is 5 to 3. So that's if I have a rectangle like this, then the ratio of the length of the width, or ratio of the length to the width, so the length is 5 to 3, so the basic rectangle would look like this, 5 to 3. Okay, now let's say I add a new rectangle. So I want to make another rectangle with the same ratio, but I want the rectangle to be slightly bigger. So let's say this rectangle is 24 centimeters wide. So obviously this is not 24 centimeters wide, but I'm limited by the space on the screen. So we'll just say the following. Let's say this is 24, and we want to know how long is it. How long is this? Okay, oops. There we go. So how long is that side? Well, I'm going to use, because this rectangle, the black rectangle, is the same as the red rectangle as far as ratio of length to width is, we can say the following. Whoops. That is black. Okay. The 5 to 3 ratio. Whoops. The 5 to 3 ratio of the original rectangle has to equal the unknown length to width ratio of the new rectangle. And when we set up a problem like this, it really just becomes a cross multiply divide type problem. So to solve for this unknown number here, we can just cross multiply 24 times 5, divide by 3, and that'll get us our unknown answer. So our unknown answer for the length is going to be 24 times 5 divided by 3, which will give us an answer of, I believe, 40. There we go. So this tells us then that this unknown length here is going to be 40 centimeters. Okay. And that's what the ratio allows us to do. It allows us to take the ratio from one object and apply it to another object to get a similar object. Not exactly the same, but the ratios of the sides of the dimensions are exactly the same. Now you might wonder, how do you set up the ratio? Well, in our problem, we had the ratio was length to width was 5 to 3. So if I go back here, I had set up the 5 to 3 like this. 5 was my length, so this is my length. This is my width. On the new rectangle, we knew the width was 24, so the width goes in the same spot on the new ratio. So we put the 24 there, and then the length, that was our unknown, like that. So if you're ever confused as to where the numbers go, just ask yourself, kind of, what side does each number correspond to? This 24 was a width, so it'll go on the width side, so it'll basically be in the same spot as the 5. This 3 is a length, so it'll go in the same spot where the unknown side is. And that's one way that's one way I think about it, is that the width goes in the same spot as other widths, length goes in the same spot as other lengths. So that way you can avoid confusion as to because sometimes some people will put the 24 up top, but it's not supposed to be there. So sometimes people will put the 24 up here, but that's not where it's supposed to go, because all the top spots are taken by lengths. All the bottom spots are supposed to be widths. That's one way you can remind yourself of how to sort that out. Alright, so moving on to the next example. Okay, so now that we have the an idea of what proportional reasoning is, we can use that to work with scale statements and scale factors. So a scale statement, as shown here, is a ratio that compares the size of a model to the original, or the size of the model to the size of the original object. So for example, a model might be given a scale statement of 3 to 5. This means that 3 units on the model represents 5 units on the original object. Right? And a lot of models are given this way. For example, if any of you do model car building, a lot of common sizes like 1/120th or 1/200th basically means that 1 unit on the, so it's taking a 1/120 scale, 1 unit on the model is actually 120 units on the original object. Or a 1/270th model, 1 unit on the model is 270 units on the actual model. Okay. Now a scale factor is the number by which the measurement of one object must be multiplied to give the measurements of the other object. It is the ratio of corresponding lengths of similar geometric figures. So what this basically means is that the scale factor is how many times bigger or how many times smaller the model is compared to the original model. Okay. As an example, if I take a model that's at 1/270th scale, this basically means that if the model, that's the model size, and this is the original size, the original is 270 times bigger than the model. Or you can also think of it as the model is 270 times smaller than the original. Alright, so that's what a scale factor is. And you can sort of see how the scale factor and scale statement and proportional reasoning kind of go hand in hand. Okay. So usually, and at least in my experiences when working with models, a lot of models will usually be given in this kind of statement where it's 1 to something, so you can easily tell how many times bigger or how many times smaller the objects are. So it's usually 1 to 270 or 1 to 100 or something like that. I don't normally see models written this way. Most models, that's just very inconvenient. In most modeling aspects, because imagine trying to build a model car and they tell you the scale is 3 to 5. It means that it's hard to tell how many times bigger the original is compared to the model in this 3 to 5 statement, as opposed to the 1 to 270 statement. 1 to 270 is much easier to tell. Alright, so let's go through the first example. So we're going to write a scale statement for the reduced or enlarged object, and we're going to calculate the scale factor used to create the reduced or enlarged object. So one easy way to determine the scale statement, so let's call it the scale statement. Scale statement. Yeah. Oops. Alright. Whoa. What's going on here? Alright. Okay, there we go. Sorry. So, scale statement, one easy way to do this is to always write it as the model size divided by the original size. Okay, that's one way to write the scale statement. So in this case, the model size is 3 centimeters, the original size is 6, so our scale statement will be 3 over 6. And if we reduce this will reduce to 1 over 2. So the model to original, if I write it as a ratio, in the ratio form will be 1 to 2. So this is the model to the original. So this tells me that the original is going to be 2 times bigger than the model. Okay, or the model is 2 times smaller than the original. That's one way to write it. Okay. Another way you could do this is sometimes even if you mix it up, let's say I'll write this one in red. Let's say you mixed it up and you decided to write original over model. There's nothing wrong with this. It just makes the ratios look slightly different. So original over model, you would end up getting 6 over 2. Oh, sorry, not 6 over 2, 6 over 3. Okay. Which is again going to be 2. If you do this in your calculator, this would be 2, but it's better to say 2 over 1. Because then when you write it in the ratio form, you would get 2 to 1, and this is going to be the original, and this is going to be the model. So it's very, very similar to when I wrote it out the first time. It's just that the numbers are switched. Here we have, in the black, we have model to original, so 1 to 2. In the red, we have original to model, 2 to 1. So it's basically the same, it's just the numbers are slightly different. Okay? So if you mess up the equation and you did original over model, no big deal. It'll actually still give you the exact same answer, just in a slightly different form. Okay, let's go through another example. Alright, so here's another one. Here we have a box. There's an original size, and then there's the model size. Alright. So our scale statement is going to be model divided by original. Alright, now notice we have there's 3 different sides we could use. We use 1, 2, 3, and those correspond to different sides on the model. So what you need to do is, it doesn't matter, we're going to assume that since this is a scale drawing and doesn't say otherwise, everything should be to scale. So all you need to do is pick a pair of one side and then the corresponding side in the other picture. So let's say I pick 3. So I'll pick the 3 side in the original. That 3 side corresponds to the 15 in the model. Because if you look at the original, there's a shorts 1, 2, 3, so shortest side, 1's the shortest side, 2's the middle length, 3's the longest side. On the model, we have 5, 10, 15. 5 is the shortest, 10 is the middle, 15 is the longest. So if 3 centimeters is the longest side in the original, that'll correspond to the longest side in the model, which happens to be 15. So when we do our equation, we put the 15 from the model in the model spot, divided by the 3 in the original, and we'll calculate this out. This will give you a ratio of, or give an answer of 5 if you do the calculator, but what we really want to do is 5 over 1. Because then we can show that the model to original ratio is going to be 5 to 1. It basically says that the model is 5 times bigger than the original. So the model 5 times bigger than the original, or the original is 5 times smaller than the model. Okay. All right. Here's one that doesn't have a picture. It just says a man in a photograph is 2 centimeters tall. His actual height is 1.8 meters. So we want to know what is the scale factor here. Well, let's draw a man. So here is a man, and let's say his height here is 2 centimeters. Okay. And in actual real life, the man is actually 1.8 meters. Okay. Well, we do the exact same thing we did for the previous problems. We take our model size, divided by the original size. In this case, the model size is 2, the original size is 1.8. One thing to note, though, is that our units are different because we have the picture is 2 centimeters, but the height is in meters. So we need to do some changing first. And the only change we need to do is make sure that everything is in the same unit. I'm going to put everything into centimeters. And so I have 2 centimeters. And the 1.8 meters, because we have 100 centimeters in every meter, 1.8, we just multiply that by 100, and that'll get me the number of centimeters. So now I have 2 centimeters over 180 centimeters. When we calculate this, we get the following. 2 divided by 180. It's best to work in fractions as much as possible, because then you can get nice, well, most problems in this class will end up giving you nice ratios like this. Okay. If you work in a decimal, this decimal will be like 0.0101 and so on. It's not very nice to work with. So working with a ratio like this is much nicer. This tells me then that if I write it as a ratio in terms of model to original, I get a ratio of 1 to 90. So the original is 90 times bigger than the model, or in this case the picture of the man. Okay. There we go. And that's how we can calculate scale factors using information given to us from the problems. Just remember, the equation is just model divided by original. And if you mess it up and go original divided by model, it doesn't make that big a difference. It just means that the numbers will be in slightly different spaces.